Suppose you need to design a machine learning model for a given fruit, whether it's an apple or an orange. This can be an issue for a farmer to pack them separately for production line and dispatch. In the machine learning approach, the input is represented by X and output as Y. The output Y can be 0 for an apple or 1 for an orange. In order to design our system, we need to collect the data from the real world. Our dataset will contain different photographs of various fruits and their labels. Once we are done with the data collection, we will train our system and then put into test with the real world, helping the farmers to distinguish between the apple and the oranges for their purpose. Let's look at the training process in more detail. As it turns out, we know many ways of training machine learning systems, each with different parameters and settings. For example, we can learn a 1 nearest neighbor system, a 3 nearest neighbor system, a 5 nearest neighbor system, a kernel regression system with a sigma 1, a kernel regression system with a sigma of 2, naive Bayes, support vector machine, and many others. The problem of choosing which method to use from a pool of possible methods is known as model selection. We want to choose the model that will learn the best at test time in the real world. But all we have is a fixed data set. One way to choose is to train each method on our data and then test on the same data that we have. This is a terrible idea. It indicates that we are giving the answer key to the model itself before even providing the test data set. Instead, we will do the following. We split our data into sections. Each section is called a fold. In this example, we have 4 folds. Next, we will iterate through the folds as following. The first iteration we train on folds 2 till 4, and then we test our method unfold 1. In this case, the algorithm has never seen fold 1 before. Next, we measure the error rate of our method on this fold. We then swap places with folds 1 and 2. Now we train unfolds 1, 3 and 4 and we test unfold. We do repeat this process for each fold, withholding that fold from training and then computing error on that fold at test time. Some folds are easier to learn than others. Finally, we combine the 4 error rates into a single average. This average is known as the cross-validation error. For any single method, cross-validation error is an estimate of how the method would perform if the data we collected is an accurate representation of the real world. We repeat the cross-validation procedure for each method we might select during training. Then we can select the model with minimum cross-validation error. In this case, 5 nearest neighbors is our best guess. For this model will be the best fruit identifier for us. Now that we have chosen our model, we can evaluate it on the real data, but what sort of performance do we expect? Do we expect exactly the same performance as our cross-validation estimates? Maybe our estimate was optimistic or maybe it was too conservative. In fact, the 17% error we found during the model selection process is almost certainly optimistic. This is because model selection has biased or estimate of test error. We chose the best cross-validation error out of many possibilities. So even if we had a pool of 1 million random classifiers, we would still expect at least one of them to have low cross-validation error purely by chance. So we need to take another look at our data. We still use cross-validation, but this time we apply cross-validation twice. First, we separate our data into 2 parts. The first part will be used for model selection and the second will be used for testing to represent the unseen world. The important point is that the world data is never touched by other model selection procedures. To perform model selection, we divide the data into folds just like before. In this case, we have 6 folds. We then perform cross-validation for each of our methods to determine an error rate. In this case, 3 nearest neighbor is a method with lowest cross-validation error. Now we can evaluate the result of model selection on our tailed out test data. This time we use all folds of training data during training. Now what does this final number estimate? In fact, it is the estimate of our entire learning process. We look at the data, we train multiple methods, and then we select the best according to cross-validation. Finally, we tested on held out data not seen by the algorithm. In other words, we achieved an estimate of how our entire learning procedure, which includes model selection as a part of training, will perform on unseen data. Again, if the world happens to be well represented by our dataset, this time our estimate of 16% is most likely conservative, since we are only using a portion of the data that we have in order to train our model. In conclusion, firstly, cross-validation is a simple and useful method of model selection. But more importantly, cross-validation is also necessary to obtain an estimate of error of our model selection method.